Hello everyone, today we will study inner product. First of all, let me introduce what is inner product. Let V be a vector space. An inner product over V is a function denoted by angle brackets. Here, the angle brackets u, v is a function that maps two vectors u and v to a scalar. This function, inner product u, v, that maps two vectors u, v to a scalar. And an inner product must satisfy all following axioms. An inner product must satisfy these four axioms for all vectors u, v, w in V, and for all scalar k. The inner product must satisfy all these four axioms for all vectors u, v, w, and for all scalar k. First axiom says inner product of u, v must be the same as inner product of v, u. Second axiom says u plus v, w, the inner product u plus v, w must be the same as the inner product of u, w plus v, w. The inner product of u plus v, w must be the same as inner product of u, w plus v, w. Here we basically distribute w to both u and v. I get u, w plus v, w. That's the second axiom. Third axiom says inner product of ku, v. Inner product of ku, v must be the same as k times the inner product of uv, which says if I pull out k, it stays the same. If I pull out k for inner product of ku plus v, I can always pull out k and get k times inner product of u, v. The fourth axiom says the inner product of v, v must always be greater than 0. The inner product of v, v must always be greater or equal to 0. And the inner product of v, v equal to 0 if and only if v is 0. The dot product, the inner product of v, v is 0 if and only if v is a 0 vector. That's the fourth axiom. So if all these four axioms are satisfied, then we say this function is called inner product. If all these four axioms are satisfied, then we say this function here is an inner product. Next, let me show you some examples. First example, let u and v be vectors in Rn, and let a function be defined as angle bracket of u, v equal to the dot product of u dot v. So define this function to be dot product u dot v for all vectors u and v in Rn. Show that the above function is an inner product. In order to show the above function is an inner product, we must show that this function satisfies all its four properties. If all these four axioms are satisfied, then the function is an inner product. But if one of the axioms is not satisfied, then the function is not inner product. If one of the axioms is not satisfied, then the function is not inner product. Let's verify these axioms one by one. First axiom, axiom 1, we must show that the inner product of u, v must be the same as v, u. We must show that the inner product of u, v must be the same as v, u. By definition, angle bracket of u, v, that's the dot product of u dot v. By definition, angle bracket of u, v is the same as dot product u dot v. And we know that for dot product, u dot v equal to v dot u. And v dot u is the same as angle bracket of v, u. So angle bracket of u, v equal to v, u. Axiom 1 is satisfied. Next, let's verify axiom 2. Axiom 2 says inner product of u plus v, w that must equal to angle bracket of u, w plus v, w. By definition here, u plus v, w is the same as u plus v dot w. By definition, u plus v, w is a sense of dot product u plus v dot w. Then for dot product, there's a distributive property. For dot product, there's a distributive property. This can be rewrite as u dot w plus v dot w. For dot product, there's a distributive property. We have u dot w plus v dot w. And we know that u dot w by definition, that's an angle bracket u comma w. And v dot w by its definition here, that's angle brackets v comma w. So axiom 2 is satisfied. Axiom 2 is satisfied. Next, let's verify axiom 3. Axiom 3 says angle bracket of ku comma v must be the same as k times angle bracket of u comma v. Let's verify axiom 3. Assume k is a scalar. Ku comma v. By definition of this function, that's the dot product ku dot v. Then for dot product, there's a property says if there's a scalar in the front, we can run the scalar by itself, take the vector u dot v. If there's a scalar times a vector in the dot product, we can run the scalar by itself, do dot product first, which means I can pull out k. I have u dot v. Then by definition of inner product, by definition of dot product, by its definition here, dot product u dot v is the same as the angle bracket u comma v. So axiom 3 is satisfied. How about axiom 4? Axiom 4 says angle bracket of v comma v must always be greater or equal to 0. V comma v equal to 0 if and only if v is 0. Now let's verify axiom 4. Let v be the vector v1, v2, vn in Rn. The angle bracket of v comma v, by definition, that's the dot product v dot v. And the dot product of v dot v is v1 square plus v2 square plus vn square. The sum of all perfect squares must be non-negative. The sum of all perfect squares must be non-negative. So it satisfies the first condition in axiom 4. Next, let's verify the second condition in axiom 4. The second condition says angle bracket of v comma v is 0 if and only if v is 0. So this statement is in the form of if and only if. We must prove in both directions. Let's first of all prove from left to right. Assume angle bracket of v comma v is 0. Then we know that by definition, angle bracket of v comma v is the dot product v dot v. And dot product v dot v is v1 square plus v2 square plus vn square equal to 0. Since every term is non-negative, if their sum is 0, that means every term must be 0. Since every term is non-negative, if their sum is 0, that means every term must be 0. So v1 square must be 0, v2 square must be 0, and vn square must be 0. Hence, v1 is 0, v2 is 0, and vn is 0. In vector v, if every component is 0, then v must be the 0 vector. If every component is 0, then v must be the 0 vector. Next, let's prove from right to left. Assume V is the zero vector. Assume V is the zero vector. So to prove that the angle bracket of V, V must be zero. Assume V is a zero vector, then every component in V must be zero. If V is the zero vector in Rn, then every component in V must be zero. The angle bracket of V, V is 0 square plus 0 square plus 0 square. The sum of all zeros must be 0. So, the angle bracket of V, V is 0, if and only if vector V is 0. Let's complete the proof of axiom 4. Since all four axioms are satisfied, then this function is an inner product. Since all these four axioms are satisfied, then this function is an inner product. Therefore, this function is an inner product. So based on this example, we see that a dot product is an inner product. A dot product in Rn is an inner product over Rn. Note, the dot product in Rn is the inner product over Rn. In general, the dot product in Rn is called a standard inner product over Rn. And the dot product in Rn is called a standard inner product over Rn. The dot product in Rn is called a standard inner product over Rn. So the standard inner product over Rn is the dot product. Next example, let U and V be vectors in R3, and their function be defined as the following. Angle bracket of U, V is 2U1 V1 plus 3U2 V2 plus 5U3 V3 for all vectors U and V in R3. Show that the above function is the inner product in R3. In order to show this function is the inner product, we must verify all its four axioms. If all four axioms are satisfied, then the function is the inner product. If one of the axioms fails, then the function is not inner product. Let's first of all verify the first axiom. So let U be the vector U1, U2, U3. Let V be the vector V1, V2, V3. Let W be the vector W1, W2, W3. And let K be a scalar. Let's first of all verify axiom 1. Axiom 1 says angle bracket of U, V must be the same as angle bracket of V, U. Angle bracket of U, V by definition, that's 2u1 v1 plus 3u2 v2 plus 5u3 v3. Since u and v, they are real numbers. If I switch their order, it makes no difference. Since u1 v1, u2 v2, u3 v3, they are real numbers. If I switch order for real numbers, it makes no difference. So that's the same as 2v1 u1 plus 3v2 u2 plus 5v3 u3. That's the angle bracket of v comma u. So SCN1 is satisfied. Next, let's verify SCN2. SCN2 says the angle bracket of u plus v comma w equal to angle bracket of u comma w plus v comma w. It's the distributive property. We distribute w to u and v. So we have u plus v comma w. Here we need to add vectors u and v first. If I add vectors u and v, the first component is u1 plus v1. Second component is u2 plus v2. And the third component is u3 plus v3. Vector w is w1, w2, w3. Then apparent definition here. Here, u1 plus v1 is the first component. w1 is the first component of the second vector. So I have twice u1 plus v1 times w1 plus 3 times u2 plus v2 times w2 plus 5 times u3 plus v3 times w3. Then distribute 2 and w1. Those are real numbers. I can distribute 2 and w1. I get 2u1 w1 plus 2v1 w1. If I distribute 3, I get 3u2 w2 plus 3v2 w2. Next, distribute 5 and w3. I get 5u3 w3 plus 5v3 w3. Next, put uw together. Put uw together. I have 2u1 w1 plus 3u2 w2 plus 5u3 w3. And put vw together. Next, put vw together. I have 2v1 w1 plus 3v2 w2 plus 5v3 w3. The first parenthesis is the angle bracket u comma w. The second parenthesis is the angle brackets v comma w. So SCN2 is satisfied. SCN2 is satisfied. Next, let's verify SCN3. SCN3 says angle bracket of ku comma v is the same as k times angle bracket of u comma v. Let's verify SCN3. Let's first of all compute angle bracket of ku comma v. When we have k times u, we multiply k to each component in u. I have ku1 comma ku2 comma ku3. That's the first vector. The second vector is v. V is the vector v1, v2, v3. Then apply its definition. I have 2 times the first component plus 3 times the second component plus phi times the third component. Now, everything here are real numbers. Everything here are real numbers. So I can pull out k. I can pull out common factor k. Since all numbers here are real numbers, I can pull out common factor k. If I pull out k, I have 2u1 v1 plus 3u2 v2 plus 5u3 v3 what's in the parentheses here? That's an angle bracket u comma v. That's an angle bracket of u comma v. So axiom 3 is satisfied. Axiom 3 is satisfied. Next, let's verify axiom 4. Axiom 4 says angle bracket of v comma v must be greater or equal to 0. And angle bracket of v comma v is 0 if and only if v is the 0 vector. So let's first of all compute angle bracket of v comma v. Angle bracket of v comma v is 2v1 squared by its definition. It's 2v1 squared plus 3v2 squared plus 5v3 squared. v1 squared is a perfect square. v2 squared is a perfect square. v3 squared is also a perfect square. Perfect square times positive constant is greater than 0. Perfect square times positive number is greater or equal to 0. Perfect square times positive number is greater or equal to 0. Since all three terms are greater or equal to 0, their sum must be greater or equal to 0. Since all three terms are greater or equal to 0, their sum must be greater or equal to 0. So it satisfies the first condition in axiom 4. Next, let's verify the second axiom. Second axiom says angle bracket of v comma v is 0 if and only if v is the 0 vector. So we must prove in both directions. For the statement of if and only if, we must prove in both directions. So first of all, assume the angle bracket of v comma v is 0. We try to prove that v is the 0 vector. If an angle bracket of v comma v is 0, we know that angle bracket of v comma v is this. Then 2v1 squared plus 3v2 squared plus 5v3 squared is 0. Since here every term is greater or equal to 0, since every term is non-negative, if their sum is 0, that means every term is 0. So 2v1 squared is 0, 3v2 squared is 0, and 5v3 squared is 0. If we solve each equation for v1, v2, v3, I have v1 is 0, v2 is 0, and v3 is 0. If we solve each equation for v1, v2, v3, we have v1 is 0, v2 is 0, and v3 is 0. In vector v, if all three components are 0, then v is the 0 vector in R3. In vector v, if all components are zeros, then v must be the 0 vector in R3. So that's one direction. The other direction, assume v is the 0 vector. We try to prove that the angle bracket of v comma v is 0. Assume v is 0. We try to prove that the angle bracket of v comma v is 0. If v is the 0 vector, then in vector v, all its components are 0. So angle bracket of v comma v, by this definition here, that's 2 times 0 squared plus 3 times 0 squared plus 5 times 0 squared, which is 0. So it satisfies the second condition of axiom 4. Since all 4 axioms are satisfied, then we say this function is the inner product over R3. Therefore, angle bracket, this function, angle bracket v comma u comma v, is the inner product over R3. That's how I prove this function is the inner product over R3. Note, this function u comma v equal to 2u1 v1 plus 3u2 v2 plus 5u3 v3. This function is called weighted dot product. It's called weighted dot product. In R3. This function is called weighted dot product in R3. This function is called a weighted dot product in R3. And in general, the function u comma v equal to w1 u1 v1 plus w2 u2 v2 plus wn un vn is called the weighted dot product in Rn. Where in this formula, W1, W2, Wn are scalars. Where W1, W2, Wn are scalars. In this formula here, U1, U2, Un is the component of vector U. V1, V2, Vn is the component of V. And W1, W2, Wn, they are scalars. And also, this weighted dot product in Rn is also inner product. And the weighted dot product in Rn is also inner product. The weighted dot product in Rn is always the inner product. Over Rn. So keep in mind that the weighted dot product in Rn is always the inner product over Rn. Next example, let A and B be two vectors in M23. Here, M23 is a set of all 2x3 matrices. So both A and B, they are 2x3 matrices. And their function be defined as the following. Angle bracket of A comma B is the trace of A transpose times B. Angle bracket of A comma B is the trace of A transpose times B for all matrices A and B in M23. Show that the above function is the inner product. In order to show this function is the inner product, we must verify these four axioms. If all four axioms are satisfied, then the function is the inner product. Otherwise, if one of an axiom fails, then the function is not inner product. So let's verify all 4 axioms. First of all, let A be the matrix A11, A12, A13, A21, A22, A23. Let B be the matrix B11, B12, B13, B21, B22, B23. And let C be the matrix C11, C12, C13, C21, C22, C23. Let ABC be 2 by 3 matrices, and let K be a scalar. Let ABC be 2 by 3 matrix, so ABC belongs to M23. Let K be a scalar. Let's verify all 4 axioms. Axiom 1. We try to show that angle bracket of A comma B is the same as angle bracket of B comma A. Angle bracket of A comma B, by definition, that's the trace of A transpose times B. What's A transpose? For A transpose in matrix A, we write rows in columns. Write rows in columns. So A transpose is A11, A12, A13 in the first column, A21, A22, A23 in the second column, times matrix B. Matrix B is B11, B12, B13, B21, B22, B23. When we multiply, what's the size of this matrix? Here, first matrix is 3 by 2. It has 3 rows, 2 columns. Second matrix is 2 by 3. It has 2 rows and 3 columns. If we multiply, the resulting matrix will be 3 rows and 3 columns. If we multiply these 2 matrices, the resulting matrix will be 3 rows and 3 columns. So take row times column. First row times first column. That's A11 times B11 plus A21 times B21. Next, rows times columns. A11 times B12, A21 times B22. Next, row times column. A11 times B13 plus A21 times B23. Next, row times column. A12 times B11 plus A22 times B21. Next, row times column. A12 times B12 plus A22 times B22. Next, rows times columns. A12 times B13 plus A22 times B23. Next, rows times columns. A13 times B11 plus A23 times B21. Rows times columns. A13 times B12. A23 times B22. Next, rows times column. A13 times B13 plus A23 times B23. This is a 3 by 3 matrix. This is a 3 by 3 matrix. When we take the trace is the sum of the main diagonal. Trace is the sum of the main diagonal. So that equal to A11 B11 plus A21 plus B21 plus A12 B12 plus A22 B22 plus A13 B13 plus A23 B23. That's the angle bracket of A comma B. Next, let's compute angle bracket of B comma A. We try to show that they are exactly the same. Angle bracket of B comma A is the trace of B transpose times A. Angle bracket of B comma A is the trace of B transpose times A. So that's the trace of B transpose times A. For trace of B transpose, in vector B, in matrix B, put rows in colors. We get B11, B12, B13 in the first column, B21, B22, B23 in the second column. Then matrix A stays the same. A11, A12, A13 in the first column, A21, A22, A23 in the second column. Then multiply. When we multiply, take rows times columns. We have B11 times A11. Let me write A first. In order to match this, let me write A first. Take row times column, I get A11 times B11 plus A21 times B21. Next, row times column, I get A12 times B11 plus A22 times B21. Next, row times column, I have A13 times B11 plus A23 times B21. Next, row times column, I get A11 times B12 plus A21 times B22. Next, rows times column, I get A12 times B12 plus A22 times B22. Next, row times column, I get A13 times B12 plus A23 times B22. Next, row times column, I get A11 times B13 plus A21 times B23. Next, row times column, I get A12 times B13 plus A22 times B23. Next, row times column, I get A13 times B13 plus A23 times B23. Again, this is a 3 by 3 matrix. For a trace of 3 by 3 matrix, we add the main diagonals together. For the trace of 3 by 3 matrix, add the main diagonal together. I have A11, B11 plus A21, B21 plus A12, B12 plus A22, B22 plus A13, B13 plus A22, B23. That's the trace of this matrix. Now let's compare. First parenthesis looks exactly the same. Second parenthesis also looks the same. The third parenthesis also looks the same. Therefore, angle bracket of A comma B is the same as angle bracket of B comma A. So, angle bracket of A comma B is the same as angle bracket of B comma A. That means axiom 1 is satisfied. Next, let's verify axiom 2. Axiom 2 says angle bracket of A comma B, A plus B comma C must be the same as angle bracket of A comma C plus angle bracket of B comma C. So, by definition, angle bracket of A comma B, angle bracket of A plus B comma C, that's the trace of A plus B transpose times C. By definition, it's the trace of the transpose of the first matrix times the second matrix. It's the trace of transpose of the first matrix times the second matrix. That's the definition of this angle bracket. And we know that A plus B transpose can be rewritten as A transpose plus B transpose times C. A plus B transpose can be rewritten as A transpose plus B transpose times C. Then I can distribute C into the parentheses. Since those are matrices, I can distribute C into the parentheses. Like a trace of A transpose times C plus B transpose times C. Then for the trace of the sum of two matrices, that the property says they equal to the trace of A transpose times C plus the trace of B transpose times C. When there are two matrices adding together, the trace of this matrix is the trace of the first matrix plus the trace of the second matrix. That's one property about trace. That's a property about trace. Then, by definition, trace of A transpose times C is the angle bracket of A comma C. Trace of B transpose times C, that's the angle bracket of B comma C. So axiom 2 is satisfied. Axiom 2 is satisfied. Next, let's verify axiom 3. Axiom 3 says angle bracket of KA comma B must be the same as K times angle bracket of A comma B. Let's verify this. By definition, angle bracket of KA comma B is the trace of KA transpose times B. By definition, that's the trace of the transpose of the first matrix times the second matrix. Then one property of transpose says KA transpose is the same as K times A transpose times B. That's K times A transpose times B. Since K is a scalar, that's trace of K times A transpose times B. Since K is a scalar, A transpose and B, they are matrices. We can multiply the matrices first and then multiply by the scalar. Next, since K is a scalar, for a trace of scalar times a matrix, I can pull on a scalar. That's one property of trace. For a trace of scalar times a matrix, I can always pull out a scalar. That's the same as K times trace of A transpose times B. And we know that trace of A transpose times B, by definition, that's the angle bracket of A comma B. So axiom 3 is satisfied. Next, let's verify axiom 4. Axiom 4 says angle bracket of a comma a is always greater than equal to 0. It says angle bracket of a comma a is always greater than or equal to 0. For angle bracket of a comma a, by its definition, that's the trace of a transpose times a. By definition, that's trace of a transpose times a. And we know that a transpose, for a transpose, in matrix A, we write rows in columns. So A11, A12, A13, write the first row in the first column. A21, A22, A23, write the second row in the second column. Times matrix A, A11, A12, A13, A21, A22, A23. That's A transpose times matrix A. If we multiply, take rows times columns. Take rows times columns. First row times first column, I get A11 square plus A21 square. Since we're looking for trace, trace is the sum of main diagonal. We don't care about the other we don't care about the other entries. We only care about the main diagonal. Trace is the sum of the main diagonal. Since we are only looking for trace, don't worry about the other entries. We only find the entries in the main diagonal. So from the second row, second column here, take second row times second column. Get A12 square plus A22 square. Don't worry about the rest. Only take care of the main entries. Only take care of the main entries. For the trace, it's only about the sum of the main diagonal. We don't care about the other entries. Now, that's the third row and the third column. Take the third row times the third column. I get A13 square plus A23 square. Then, for the trace of this matrix, we add the matrix and entries in the main diagonal. For the trace of this matrix, we add entries in the main diagonal. I have A11 square plus A21 square plus A12 square plus A22 square plus A13 square plus A23 square. Here we can see that every term is a perfect square. Since every term is a perfect square, they are all non-negatives. They are all non-negative. If every term is non-negative, their sum must be non-negative. So this sum must be greater than or equal to 0. So angle bracket of a comma a is always greater than or equal to 0. That satisfies the first condition of axiom 4. Next, let's try to verify the second condition of axiom 4. The second condition says angle bracket of v comma v is 0 if and only if v is the 0 vector. So let's prove in both directions. This statement is in the case of if and only if. Let's prove in both directions. First of all, assume the angle bracket of a comma a is 0. I'm trying to prove that a is the 0 vector, which means a is the 0 matrix. Assume angle bracket of a comma a is 0. And then we know that angle bracket of a comma a, angle bracket of a comma a is this. So A11, A12, A11 square plus A12 square. Plus A12 square plus A22 square. Plus A13 square plus A23 square. That's an angle bracket of a comma a. Assume this is equal to 0. Since every term here is a perfect square, perfect square must be non-negative. Since every term is non-negative, and their sum is 0, that means every term must be 0. Since every term is non-negative, and their sum is 0, that means every term must be 0. So a11 squared must be 0. a12 squared must be 0. That should be a21. a21 squared must be 0. This is a12. a12 squared must be 0. a22 squared must be 0. a13 squared must be 0. And a23 squared must be 0. So if I take square root, that means a11 must be 0, a21 must be 0, a12 must be 0, a22 must be 0, a13 must be 0, and a23 must be 0. In matrix A, if every entry is 0, then A is the 0 matrix. In matrix A, if every entry is 0, then A must be the 0 matrix. That's one deduction. On the other deduction, assume A is a 0 matrix. Assume A is a 0 matrix, then angle bracket of A comma A equal to the trace of A transpose times A. Since A is a 0 matrix, transpose of 0 matrix is also 0 matrix. That's trace of 0 matrix times 0 matrix. This 0 matrix is 3 by 2 matrix. This 0 matrix is 2 by 3 matrix. This 0 matrix is 3 by 2 matrix. This 0 matrix is 2 by 3 matrix. And then the product of 0 matrix is 0 matrix. That's a trace of 0 matrix. This 0 matrix is 3 by 3 0 matrix. And the trace of 0 matrix is 0. The trace of 0 matrix is 0. The trace of 0 matrix is 0. Therefore, angle bracket of A comma A is 0. Since all four axioms are satisfied, then above function is an inner product. Therefore, the function angle bracket of A comma B equal to trace of A transpose times B is the inner product. Over M23. Let's complete the proof. And keep in mind, in general, this function A comma B equal to the trace of A transpose times B is always the inner product in MMN. It's always the inner product in MMN. For all m by n matrices, the proof is very, very similar. This function is always the inner product MMN. It works for all size, any size of matrices. The proof is very, very similar. And the above function, the above inner product is called the standard inner product. This inner product is the standard inner product MMN. This inner product is the standard inner product over MMN. This inner product is a standard inner product over MMN. So in general, this function is always the inner product over MMN. And this inner product is the standard inner product over MMN. Next example, let A be an invertible n by n matrix, and let U and V be vectors in Rn. Let a function be defined as the following. Angle bracket of U comma V equal to the dot product of AU dot AV for all vectors U and V in Rn. Show that the above functions is the inner product over Rn. In order to show this function is the inner product, we must show that the function satisfies all its four axioms. So let's verify all four axioms. Let U, V, W be vectors in Rn, and let K be a scalar. We try to verify all four axioms. Axiom 1, we try to verify that angle bracket of U comma V equal to the angle bracket of V comma U. Angle bracket of U comma V, by definition, that's AU dot AV. And since this is a dot product, by a property of dot product, we can switch orders. That's the same as AV dot AU. And we know that AV dot AU, by definition, that's the angle bracket of V comma U. So it satisfies the first axiom of the inner product. It satisfies the first axiom of inner product. Next, let's verify the second axiom. Second axiom try to verify that angle bracket of U plus V comma W equal to the angle bracket of U comma W plus V comma W. Here, by definition, angle bracket of U plus V comma W is A times the first vector dot A times the second vector. Then by the property of matrices, I can distribute A into the premises. Those are matrices. By the property of matrices, I can distribute A into the premises. I get AU plus AV dot AW. Then this is a dot product. By the property of dot product, I can distribute AW into the premises. By the property of dot product, I can distribute AW into the premises. I get AU dot AW plus AV dot AW. Then by the definition of this, by this definition here, AU dot AW, that's the angle bracket of U comma W. AV dot AW, by the definition here, that's angle bracket of V comma W. So axiom 2 is satisfied. Axiom 2 is satisfied. Next, let's verify axiom 3. We try to verify that angle bracket of KU comma V equal to K times angle bracket of U comma V. By definition, it can be written as A times the first vector dot A times the second vector. Since A and U, they are matrices, K is a scalar, I can pull out K. That can be written as K times AU dot AV. Here, this is a dot product, k is a scalar, I can pull out k. By the property of dot product, I can pull out k. It can be written as k times au dot av. And we know that au dot av, by this definition here, that's angle bracket of u comma v. So axiom 3 is satisfied. Next, let's verify axiom 4. Axiom 4 should show that angle bracket of v comma v is non-negative. Angle bracket of v comma v, by definition, that's av dot av. Then, by the property of dot product, the vector dot itself is always greater or equal to 0. By the property of dot product, the vector dot itself is always greater or equal to 0. That's a property of dot product. A vector dot itself is always greater or equal to 0. That's a property of dot product. A vector dot itself is always greater or equal to 0. So the first condition of axiom 4 is satisfied. Next, let's verify the second condition of axiom 4. It says angle bracket of v comma v is 0 if and only if v is the 0 vector. Let's prove in both directions. First of all, let's assume angle bracket of v comma v equal to 0. Then, by definition of angle bracket, that means av dot av is 0. That means av dot av is 0. Then, by a property of dot product, if a vector dot itself is 0, that means the vector itself must be 0. By a property of dot product, if a vector dot itself is 0, that means the vector itself must be 0. Here we treat av as a vector. If a vector dot itself is 0, then the vector itself must be 0. That's a property of dot product. If a vector dot itself is 0, then the vector itself must be a 0 vector. If a vector dot itself is 0, then the vector must be a 0 vector. That's a property of dot product. If AV is 0, since A is irrotable, I can multiply both sides by inverse of A. Since matrix A is irrotable, I can multiply both sides by inverse of A. Hence, V is the 0 vector. Inverse A cancels A. I get V by itself on the left side. On the right side, inverse of A times 0 vector is 0. So V is the 0 vector. On the other direction, assume V is a 0 vector. We try to prove that angle bracket of V comma V is 0. Assume V is 0. We try to prove that angle bracket of V comma V is 0. Assume V is 0, then AV must be 0. A times the 0 vector must be 0. Angle bracket of V comma V, by definition, angle bracket of V comma V is AV dot AV. And we know that AV is 0. 0 vector dot 0 vector is 0. That completes the proof for axiom 4. So axiom 4 is also satisfied. Since all 4 axioms are satisfied, this function is an inner product. Since all 4 axioms are satisfied, this function u comma v equal to au dot av is the inner product. over Rn. Note, the above inner product is called the inner product of Rn. Generated by matrix A. This inner product is called inner product of Rn, generated by matrix A. Next example, let f and g be vectors in Pn, and let a function be defined as the following. Angle bracket of f comma g is a0 times b0 plus a1 times b1 plus an times bn. So the angle bracket of f comma g is a0 times b0 plus a1 times b1 plus an times bn for all vectors f and g in Pn. For all vectors f and g in Pn, show that the above function is the inner product over Pn. In order to show this function is inner product over Pn, we must show that this function satisfies all these four axioms. If all these four axioms are satisfied, then the function is the inner product. Otherwise, if one of the axioms is not satisfied, then the function is not inner product. So let's check all four axioms. First of all, assume f equal to f of x equal to a0 plus a1x plus ansn. G equal to g of x equal to b1 plus b1x plus bnxn, and h equal to h of x equal to c0 plus c1x plus cn times x to the power n. Let fgh be vectors in Pn, and let k be a scalar. Let k be a scalar. Let's first of all verify the first axiom. Angle bracket of f comma g, which will show that they equal to the angle bracket of g comma f. By definition, angle bracket of f comma g equal to a0 times b0 plus a1 times b1 plus an times bn. Here, the a's and the b's they are real numbers. For real numbers, if we switch order, it makes no difference. So it can be rewrite as b0 times a0 plus b1 times a1 plus bn times an. That's an angle bracket of g comma f. So axiom 1 is satisfied. Next, let's verify axiom 2. Axiom 2 to verify that angle bracket of f comma g, angle bracket of f plus g comma h, we shall show that they equal to the angle bracket of f comma h plus g comma h. So if I add f and h, f and g together, if I add f and g together, f plus g is a0 plus b0 plus a1 plus b1 times x plus an plus bn times x to the power n. That's f plus g. H is c0 plus c1x plus Cn times Xn. So that's f plus h. That's f plus g, comma h. That's h. Then, by the definition, when we apply this function, we multiply the corresponding components, multiply the corresponding coefficients. I have a0 plus b0 times c0. We multiply the corresponding components. a1 plus b1 times c1 plus an plus bn times cn. Those are real numbers. Here a, b, c, they are all real numbers. I can distribute. If I distribute, I get a0 c0 plus b0 times c0 plus a1 c1 plus b1 c1. Plus an cn plus bn cn. Next, put ac together. Put every term of ac together. I have a0 c0 plus a1 c1 plus an cn. Then put bc together. Put the terms of bc together. I have b0 c0 plus b1 c1 plus bn cn. Then, by the definition of this function, a0 c0 plus a1 c1 plus an cn, that's an angle bracket of f comma h, because a's are the coefficient of function f, c's are the coefficient of function h. Then b0 c0 plus b1 c1 plus bn cn, that's an angle bracket of g comma h, because the b's are the coefficient of function g, and the c's are the coefficient of function h. So here we have angle bracket of f plus g comma h equal to an angle bracket of f comma h plus g comma h. So SCN2 is satisfied. Next, let's verify SCN3. For SCN3, we try to verify that angle bracket of kf comma g, angle bracket of kf comma g is equal to k times angle bracket of f comma g. Here we multiply kf first. When we multiply kf, we multiply k to every term of function f. When we multiply kf, we multiply k to every term here in function f. If I multiply k to f, I have ka0 plus ka1x plus kanxn. That's function kf. Then for function g, the function g here is b0 plus b1x plus bnsn. That's function kf. That's function g. Then when we apply this function, angle bracket, we multiply the corresponding components, multiply the corresponding coefficients. I have ka0 times b0 plus ka1 times b1 plus kan times bn. Here, since k, a, b, they are all real numbers, so I can factor, pull out k. Since they are all real numbers, I can factor, pull out k. If I pull out k, I get a0, b0 plus a1, b1 plus an, bn. Then by definition, a0, b0 plus a1, b1 plus an, bn, that's an angle bracket of f comma g. So SCN3 is satisfied. Next, let's verify SCN4. SCN4 has two parts. First part, it says angle bracket of f comma f must be non-negative must be greater or equal to 0. Let's verify the first condition first. Angle bracket of f comma f. We multiply the corresponding components. First coefficient in function f. First coefficient is a0. a0 times a0 is a0 squared. Second coefficient is a1. a1 times a1 is a1 squared. And then continue, eventually we have an squared. Here, this every term is a perfect square. A perfect square is non-negative. The sum of non-negative numbers must be non-negative. Since every term is non-negative, the sum of non-negative numbers is non-negative. So the sum here is greater than or equal to 0. That satisfies the first condition in axiom 4. Now the second condition in axiom 4. Angle bracket of f comma f is 0 if and only if f is the zero vector. Let's prove from left to right first. We assume angle bracket of f comma f is 0. We try to prove that f is the zero vector. Assume angle bracket of f comma f is 0. We try to prove that f is the zero vector. Now, angle bracket of f comma f is this a0 squared plus a1 squared plus an squared. That's the angle bracket of f comma f. Since that's 0, we have a0 squared plus a1 squared plus an squared equal to 0. Then here, since every term is non-negative, if their sum is 0, that means every term must be 0. Since every term is non-negative, if their sum is 0, that means every term must be 0. So a0 squared must be 0, a1 squared must be 0, and eventually an squared must be 0. If I take square root, I have a0 equal to 0, a1 equal to 0, and an equal to 0. If I take square root, a0 is 0, a1 is 0, and an is 0. Since every coefficient in function f is 0, f must be 0. Since a0, a1, an they are all zeros, f must be 0. So f must be 0. That's one direction. Next direction, assume function f is 0. We try to prove that the angle bracket of f comma f is 0. Assume f is 0. If a function is 0, that means all its coefficient must be 0. If a polynomial is 0, that means all its coefficient must be 0. So a0 must be 0, a1 must be 0, and an must be 0. We know that angle bracket of f comma f is a0 squared plus a1 squared plus an squared. Since a0 is 0, a1 is 0, an is 0, their sum must be 0. Since a0 is 0, a1 is 0, an is 0, their sum must be 0. So that's the other deduction. If f is 0, then angle bracket of f comma f is 0. So axiom 4 is also satisfied. If all these four axioms are satisfied, this function is the inner product over Pn. Therefore, this function f comma g, angle bracket of f comma g, equal to a0 b0 plus a1 b1x plus a1 b1 plus an bn is the inner product over Pn. So that complete the proof of this theorem. That complete the proof. Note, The above inner product, this inner product, is called a standard inner product over Pn. This inner product here is called a standard inner product over Pn. The above inner product is the standard inner product over Pn. This inner product is the standard inner product over Pn. Next example, let f and g be vectors in CAB. Here, this symbol CAB, it means the set of all continuous functions on the interval from a to b. The set of all continuous functions on the interval from a to b. And let a function be defined as the following. Angle bracket of f comma g is the integral from a to b, f of x times g of x dx, for all vectors f and g in CAB. Show that the above function is the inner product over CAB. Here, CAB is the set of all continuous functions on the interval from a to b. In order to show this function is the inner product, we must show that this function satisfies all these 4 axioms. If all 4 axioms are satisfied, then the function is the inner product. Otherwise, if one of the axioms is not satisfied, then the function is not inner product. So let's prove it. First of all, let f, g, and h be functions in CAB. So let f, g, h be continuous function on the interval from a to b. Let k be a scalar. Axiom 1 says angle bracket of f comma g must be the same as angle bracket of g comma f. By definition, angle bracket of f comma g is the integral from a to b, f of x times g of x dx. And since f of x, g of x, they are real valued functions, I can switch their orders. If I switch f and g, make no difference. That's the same as g of x times f of x dx. This is the angle bracket of g comma f. So axiom 1 is satisfied. Next, let's verify axiom 2. Axiom 2 says f plus g comma h must be the same as angle bracket of f comma h plus angle bracket of g comma h. Here, by definition, f plus g comma h, that can be written as integral from a to b, f of x plus g of x times h of x dx. Then, since f, g, h, they are real valued functions, I can distribute h. I get f of x times h of x plus g of x times h of x dx. Then, by a property of definite integral, I can separate it into two integrals. Integral from a to b, f of x times h of x dx, plus integral from a to b, g of x times h of x dx. Then, by the definition of this function here, the first integral can be rewritten as angle bracket of f comma h. The second integral can be rewritten as g comma h, angle bracket of g comma h. So axiom 2 is satisfied. axiom 2 is satisfied. Next, let's verify axiom 3. Axiom 3 says angle bracket of kf, comma g, it must equal to k times angle bracket of f, comma g. Here, by the definition of this function, this angle bracket can be rewritten as integral from a to b k times f of x times g of x dx. This angle bracket can be rewritten as integral from a to b k times f of x times g of x dx. Then here, since k is a constant, I can bring k out of integral. It can be rewritten as k times integral from a to b f of x g of x dx. Then for integral from a to b f of x g of x dx, by the definition of this function, they equal to angle bracket of f, comma g. So axiom 3 is satisfied. Next, let's verify axiom 4. Axiom 4 has two conditions. First condition says angle bracket of f, comma f must be non-negative. It must be greater than or equal to 0. Angle bracket of f, comma f, by definition of this function, we plug in f for f, plug in the other f for g. That's the integral from a to b f of x times f of x dx. That's the integral from a to b f of x square dx. Since f of x square is always greater than or equal to 0, then by a property of definite integral, this definite integral is always greater than or equal to 0. Here, since the integrand is non-negative, this definite integral is always non-negative. So it satisfies the first condition in axiom 4. Next, let's verify the second condition in axiom 4. The second condition is the if and only if statement. The second condition in axiom 4 is the if and only if statement. We must verify in both directions. First of all, assume angle bracket of f, comma f equal to 0. We try to prove that f is 0. We know that angle bracket of f, comma f is the integral from a to b f of x squared. Since this function is non-negative, it's always above x-axis, and the total area under the curve is 0. That means there's no area under the curve. This integral represents the area under the curve. Since this curve is always non-negative, so this curve is always above x-axis. If this curve is always above x-axis and there's no area under the curve, that means this curve must be a 0 function. This function here represents the curve, and the integral represents area under the curve. Since this curve is above x-axis, and there's no area under the curve, that means this curve must be a 0 function. If I take square root, f of x must be 0. So, angle bracket of f, comma f equals 0 implies that f is 0. Next, let's try to prove on the other direction. Assume f is 0. We try to prove that the angle bracket of f, comma f is 0. Angle bracket of f, comma f, by its definition here, let's integral from a to b f of x squared dx. Since f of x is 0, I get integral from a to b, 0 dx. And we know that definite integral of a constant, definite integral of 0 is 0. Definite integral of 0 is 0. So the angle bracket of f comma f is 0. So both conditions in SCM 4 are satisfied, which means SCM 4 is satisfied. Since all 4 SCMs are satisfied, this function is the inner product over CAB. Therefore, this function is the inner product over the vector space CAB. So this function is the inner product over the vector space CAB. Let's complete the proof. Next, let me show you some properties of inner product. Let UVW be vectors in a real inner product space V. Real inner product space means we only consider real numbers. For the inner product, we only consider real numbers. And let K be a scalar. Then we have the following properties. Property A says inner product of 0, V is 0. Here, this 0 is not 0 vector, and this 0 is a scalar. This 0 is not 0 vector, and this 0 is a scalar. B says inner product of U minus V, W is inner product of UW minus VW. Part C says inner product of U, V plus W is U, V, inner product of U, V plus inner product of U, W. Part D says inner product of U, V minus W is the inner product of UV minus inner product of UW. So for B, C, D here actually we distribute. For part B, I distribute W to U and V. For part C, I distribute U to V and W. For part D, also I distribute U to V and W. And for part E, inner product of U, KV. If K is a scalar of V, I can pull out K. That's the same as K times inner product of UV. Now let's prove it. When we prove these properties, we can use these theorems of inner product space. We have these 4 theorems. We'll use these 4 theorems to prove these properties. Let's prove for property part A first. For property A, we try to prove that inner product of 0, V equal to 0. This 0 is a 0 vector. We know that 0 vector can be rewritten as 0 plus 0. 0 vector can be rewritten as 0 plus 0. Leave the left side the same. Leave the left side the same. On the right side, we have 0 plus 0, V. By SCM 2, when we have inner product of U plus V, W, I can distribute W to both U and V from right side. I can distribute W to both U and V. So do the same thing here. By SCM 2, I distribute V to both zeros. I get inner product of 0, V plus inner product of 0, V. By SCM 2. By SCM 2, I get this. Then here, in this equation, I can subtract both sides. I can subtract both sides by 0, V. So I get 0 equal to the inner product of 0, V. That proves property part A. Inner product of 0, V is 0. inner product of 0, v is 0. Part B. Let's prove that inner product of u minus v, w equal to the inner product of u, w minus v, w. Inner product of u minus v, w, it can be rewritten as u plus negative v, w. U minus v can be rewritten as u plus negative v, w. Then, by SCN 2, when we have two vectors acting together in the first part, I can distribute w to both of them. So distribute w to both of them. I get inner product of u, w plus inner product of negative u, w. That's by SCN 2. Next, I leave u, w the same. We know that negative v can be rewritten as negative 1 times v. Negative v can be rewritten as negative 1 times v, w. Then I can pull out negative 1. By axiom 3, if there's a scalar in front of the first vector, I can pull out a scalar. So by axiom 3, I can pull out negative 1. I get u, w plus negative 1 times the inner product v, w. That's by axiom 3. And we know that a scalar plus negative 1 times another scalar, that's u, w minus v, w. That's property part B. Next, let's prove property C. For property C, we try to prove that inner product of u, v plus w is inner product of u, v plus inner product of u, w. How can we prove it? Inner product of u, v plus w. I can first of all switch the first and the second vector. So put v plus w in the front, put u on the back. That's SCN 1. For SCN 1, I can interchange two vectors. By SCN 1, I can interchange two vectors. That's by SCN 1. Then u plus w, v plus w, u. By SCN 2, I can distribute second vector to the first vector. I can distribute the second vector to the first vector here. Distribute w to u and v. Here I can distribute u to v and w. I get v, u plus w, u. That's by SCN 2. It's almost the same as what we have here. We want to have u, v plus u, w. But we have u on the back. So again, by SCN 1, I can interchange the first and the second vector. By SCN 1, v, u is the sense u, v. And W comma U is in a sense U comma W. That's again by SCM 1. That's part C. Next, part D. I'll try to prove that inner product of U comma V minus W is the inner product of U comma V minus U comma W, which is in a sense saying I distribute U to both of them. I distribute U to V and W. How can we prove it? U comma V minus W. By SCM 1, I can put the second vector in the front. I can write V minus W in the front and write U on the back. That's by SCM 1. By SCM 1, I can interchange in the first and the second vector. Then we have V minus W, comma U. Then by property part B, we prove B already. So in part, we prove B already. So in part D, I can use B to prove D. Since we prove B already, when we prove part D, I can use B to prove D. Property B says when we have U minus V comma W, we can distribute the second vector to both of them. So distribute the second vector to both of them. We get V comma U minus W comma U. That's by property part B. That's by property B. I distribute the second vector to the first vector. Subtraction stays the same. That's part D. E. I'm trying to prove that U comma KV is K times inner product of U comma V. Which means if the second vector has a component in the front, if the second vector has a scalar in the front, I can pull a scalar. If the second vector has a scalar, I can pull it outside. Let's prove it. Inner product of U comma KV. By SCM 1, I can interchange in the first and the second vector. I get inner product of KV comma U. That's by SCM 1. By SCM 1, I can interchange the first and the second vector. Next, we have KV comma U here. That's the inner product of KU comma V. That's the inner product of KV comma U. By SCM 4, by SCM 3, SCM 3 says if there's a scalar in front of the first vector, I can pull a scalar. If there's a scalar in front of the first vector, I can pull a scalar. Here we have a scalar in front of the first vector, so I can pull a scalar. I get K times inner product of V comma U. That's by axiom 3. That's by axiom 3. If there's a scalar in front of the first vector, I can pull on a scalar. But that's almost the same as we have here. We need K times inner product of U comma V. Here we have K times inner product of V comma U. So again, by SCM 1, I can interchange U and V. By SCM 1, I can interchange U and V. That's exactly what we have here. So let's prove for these properties. Keep these properties in mind. Next, let me introduce long and distant. Let V be a real inner product space, and let U and V be vectors in V. The long vector V, denoted by this symbol, double bars with a V inside. The norm V is defined as norm V equal to square root of inner product of V comma V. Norm V is defined as square root of inner product of V comma V. Or it's the same as saying norm V squared equal to the inner product of V comma V. The distance between vectors u and v denoted by d of uv. The distance between vectors u and v denoted by denoted by d of u and v is defined as distance from u to v is the norm of vector u minus v. Distance from u to v is the norm of vectors u minus v. So keep it in mind. That's how we define norm and distance. Next, let's look at some examples. Let A be an invertible matrix. You can verify by yourself. This matrix A is invertible by taking determinant. You can take determinant for matrix A. You can see that the determinant is not 0. So this matrix A is invertible. Let A be an invertible matrix. Let the inner product u comma v equal to au dot av. Let the inner product u comma v equal to au dot av. This is a dot product. Then this inner product be the inner product generated by matrix A on R3. Assume u is the vector 3, 2, negative 1. V is the vector 1, 0, 1. Find the norm of u, norm of v, and distance from u to v. Find the norm of u, norm of v, and the distance from u to v. How can we find norm of u? By definition, norm of u is square root of the inner product of u comma u. Norm of u, by definition, is square root of the inner product of u comma u. And the inner product here is defined by au dot av. For inner product of uv, it's defined as au dot av. Since both vector here is u, we have au dot au. We have inner product au dot au. But what's au here? For au, take matrix A times vector u. Take matrix A times vector u. Here A is the matrix 1, 2, 3, 0, 1, 1, 2, 1, 2 times vector u. Here we write vector u as a column vector. We have 3, 2, negative 1. Then multiply. Take row times column. Take row times column. 3 plus 4 is 7. 7 minus 3 is 4. Row times column. 0 plus 2 minus 1 is 1. Next, take row times column. 6 plus 2 is 8. 8 minus 2 is 6. So AU is a vector 4, 1, 6. AU is a vector 4, 1, 6. So we have the dot product of 4, 1, 6 dot 4, 1, 6. Here we have the dot product vector 4, 1, 6 dot 4, 1, 6. When we calculate dot product, we multiply the corresponding components. 4 times 4 is 16. 1 times 1 is 1. 6 times 6 is 36. Square root of 16 plus 1 plus 36 is 53. That's norm of vector u. Now how about norm of vector v? By definition of norm vector v is square root of inner product of v comma v. And by the definition of this inner product here, u comma v is au dot av. So inner product of v comma v will be av dot av. What's av here? For av here, take matrix A times vector v. Here matrix A is 1, 2, 3, 0, 1, 1, 2, 1, 2. V is the vector 1, 0, 1. Multiply. Take row times column. 1 plus 0 plus 3. It's 4. 1, 0 plus 0 plus 1 is 1. 2 plus 0 plus 2 is 4. I get a vector 4, 1, 4. That's AV. So here, AV is the vector 4, 1, 4. So take 4, 1, 4 dot 4, 1, 4. When we calculate dot product, we multiply the first component to the first component, second component to the second component, and the third component to the third component. We get 16 plus 1 plus 16. That's square root of 33. That's the norm of vector v. That's the norm of vector v. Next, how can we compute distance from u to v? For distance from u to v, by definition, distance from u to v is the norm of u minus v. So by definition, it's the norm of u minus v. Here we must compute u minus v first. What's u minus v here? U minus v, take vector u minus vector v. U is the vector 3, 2, negative 1. V is the vector 1, 0, 1. If I subtract here, I get a vector 2, 2, negative 2. Let me call this vector w. So distance from u to v is the same as norm of w. Then for norm of w, by definition of norm, that's square root of inner product of w comma w. And we know that by definition of inner product here, inner product of u comma v is au dot av. So for inner product of w comma w, that's aw dot aw. What's aw? A is the matrix 1, 2, 3, 0, 1, 1, 2, 1, 2. W is the vector 2, 2, negative 2. Let's multiply. Take row times column. 2 plus 4 is 6. 6 minus 6 is 0. 0 plus 2 minus 2 is also 0. 0 plus 2 minus 2 is also 0. Take row times column. 4 plus 2 is 6. 6 minus 4 is 2. So AW is a vector 0, 0, 2. So here, distance between u and v is norm of w, which is this square root of aw dot aw. That's square root of 0, 0, 2 dot 0, 0, 2. Take dot product here. I have square root of 0 plus 0 plus 4. 0 plus 0 is 0. 0 plus 4 is 4. So distance between u and w, between u and v, is 4. Next example, for all functions f and g in C0, 3, here, the vector space C0, 3 is the set of all continuous functions on the interval from 0 to 3. That's the set of all continuous functions on the interval from 0 to 3. Their inner product on C0, 3 be defined as inner product of f, g is the integral from 0 to 3 f of x times g of x dx. Assume function f is x plus 2 and function g is 2x plus 1. Find the normal function f, normal function g, and the distance from f to g. Let's find the normal function f first. For normal function f, to make it a little easier, let's find norm of f squared first. We know that the norm square of a norm is the inner product of this vector. So norm of f squared is the inner product of f, f. Then, by the definition of inner product, that's the integral from 0 to 3 f of x times f of x. We plug in both f for this function. Dx. What's function f here? Here function f is x plus 2. So you get s plus 2 times s plus 2 dx. Next, solve this integral. Let me multiply everything out first. If I multiply everything out, I get s squared plus 4x plus 4 dx. If we take antiderivative, we get s cubed over 3 plus 4x squared over 2 plus 4x. Evaluate from 0 to 3. If we plug in 3 cubed is 27. 27 over 3 is 9. If I plug in 3 here, 3 squared is 9. 9 times 4 is 36. 36 divided by 2 is 18. If I plug in 3 here, 3 times 4 is 12. That's 39. So norm of f squared is 39, which means norm of f is square root of 39. Next, let's find norm of g. Do the same thing. Let's compute norm of g squared first. Norm of g squared, by definition of norm, that's inner product of g, g. Then, by this definition here, inner product of g, g is integral from 0 to 3 g of x times g of x dx. Here, g of x is 2x plus 1. Next, let's solve the integral. In order to solve this integral, let's multiply everything out first. If we multiply everything out, we have 4x squared plus 4x plus 1 dx. Then take antiderivative. I get 4x cubed over 3 plus 4x squared over 2 plus x. Evaluate from 0 to 3. If I plug in 3 cubed is 27. 27 over 3 is 9. 9 times 4 is 36. If I plug in 3 here, 3 times 3 squared is 9. 9 times 4 is 36. 36 divided by 2 is 18. If I plug in 3 here, I get 3. If I plug in 0, I get 0 everywhere. Next, adding up. 36 plus 18 is 54. 54 plus 3 is 57. So ln of g squared is 57, which means ln of g is square root of 57. Next, let's compute distance from f to g. For the distance from f to g, by definition of distance, that's ln of vector f minus g. What's f minus g here? F minus g, take function f minus function g. That's x plus 2 minus 2x plus 1. If we combine like terms, x minus 2x is negative x. 2 minus 1 is 1. So distance from f to g is ln of negative x plus 1. Next, let's compute ln of negative x plus 1 square. Let's compute square first. By definition of ln of negative x plus 1 square is the inner product of negative x plus 1 comma negative x plus 1. So here we have two functions inside the inner product. By this definition, we take integral from 0 to 3, take the first function times the second function. That's the integral from 0 to 3. We take the first function times the second function. Then we try to solve this integral. We can multiply everything out first. If we multiply everything out, we get s squared minus 2x plus 1. Next, take antiderivative. We get s cubed over 3 minus 2s squared over 2 plus x. Evaluate from 0 to 3. If we plug in 3 cubed is 27. 27 over 3 is 9. If we plug in 3 here, 3 squared is 9. 2 over 2 and 2 cancel, so we get negative 9 here. If I plug in 3 here, I get 3. Together, 9 minus 9 plus 3 is 3. So that's the ln of negative x plus 1 squared. We know that distance from f to g is the ln of negative x plus 1, which is square root of 3. 3 is negative x plus the ln of negative x plus 1 squared. So for the ln of negative x plus 1, we take square root. We get net square root of 3. So that's the distance from f to g. That's the distance between these two functions, f and g. Next, let me show you some properties about ln and distance. Let V be a real inner product space, and let U and V be vectors in V, and let K be a scalar. Then we have the following properties. First property says ln of V is always greater than or equal to 0. Ln of V equal to 0 if and only if V is 0. B says ln of KV is always absolute value of K times ln of V. C says distance from U to V is the same as the distance from V to U. Part D says distance from U to V is always greater than or equal to 0. Distance is always non-negative. And the distance between U and V is 0 if and only if U equal to V. Now let's prove it. Let's prove part A first. In part A, we try to prove that norm of V is always greater than or equal to 0. We know that norm of V, by its definition, that's square root of the inner product of V comma V. And we know that square root of any positive number is always positive. By axiom 4, we know that inner product of V comma V is always non-negative. Square root of non-negative number is always non-negative. Square root of non-negative number is always non-negative. It cannot be negative. Next, we try to prove that norm of V is 0 if only if V is 0. We know that norm of V is 0 if and only if norm of V is 0 if and only if norm of V squared is 0. And we know that norm of V squared is the inner product of V comma V. Norm of V squared is the inner product of V comma V. And by axiom 4, we know that inner product of V comma V is 0 if only if V is 0. Inner product of V comma V is 0 if and only if V is 0. So by axiom 4, we know that inner product of V comma V is 0 if and only if V is 0. So that's by axiom 4. So by this we prove that norm of V is 0 if and only if V is 0. That complete the proof for part A. Next, let's prove part B. Part B, we try to prove that norm of KV equal to an absolute value of K times norm of V. What's norm of KV? For norm of KV, by definition, that's square root of KV, square root of the inner product of KV comma KV. Next, by axiom 3, it says, if the first vector has a component, I can pull it outside. Axiom 3 says, if the first vector has a component, I can pull it outside. If the first vector has a scalar, I can pull it outside. So, by axiom 3, I pull out the first K. By axiom 3, I can pull out the first K. I get K times V comma KV. That's by axiom 3. I pull out a scalar from first vector. Next, by property of inner product E, by the property of inner product part E, I can pull out a scalar from second vector to the front. By property of inner product part E, I can pull out a scalar from the second vector. So I can pull out a second K from here. Next, by the property of inner product part E, I can pull out the scalar from second vector. If I pull out this K, I get K squared times inner product of V comma V. And we know that inner product of V comma V is norm of V squared. If I take square root for square, K could be either, since K is either positive or negative, when we take square root for square, I get absolute value of K. And since norm of V is always positive, square root cancel square. Since norm of V is always positive, square root cancel square. I get norm of V here. That complete the proof for part B. So norm of KV is always absolute value of K times norm of V. Part C. We try to prove that distance from UV is the same as the distance from V to U. Here, distance from U to V, by its definition, That's norm of vector u minus v. We try to prove that this distance from u to v is the same distance from v to u. Let me try to switch order for u and v. How can we switch order for u and v here? U minus v can be rewritten as -1 times v minus u. Vectors u minus v can be rewritten as -1 times v minus u. Then, by part B, if there's a scalar multiplied by a vector in a norm, if we have a scalar times a vector, I can pull the scalar and put absolute value in the front. So by part B, when we have a norm of a scalar times a vector, I can pull the scalar by putting absolute value in the front times the norm of the vector v minus u. We know that norm of -1 is 1. And 1 times norm of u, 1 times norm of v minus u is norm of v minus u. Then by definition of distance, that's the distance from vector v to u. That complete the proof for part C. Now how about part D? Part D says distance from u to v is always greater or equal to 0. We know that distance from u to v is always the norm of vector u minus v. By property A, norm of any vector is always greater or equal to 0. We can treat this as one vector. Norm of this vector is always greater or equal to 0. That's by part A. By part A, the norm of any vector is always greater or equal to 0. When we prove part D, we can use something already been proved. When we prove part D, we can use something already been proved. Here I'm using part A to prove part D. So distance from u to v is the norm of the vector u minus v. And by part A, we know that the norm of any vector is always greater or equal to 0. Next, try to prove that distance from u to v is 0 if and only if u equal to v. We know that distance of u comma v is 0. By definition of distance, that means the norm of vector u minus v is 0. That's by definition of distance. We have this. Next, we can treat u minus v as one vector. Then the norm of the vector is 0 if only if the vector inside is 0. The norm of the vector is 0 if and only if the vector inside is 0. So if the norm of this vector is 0, by part A, the norm of vector u minus v is 0 if and only if u minus v is 0. And we know that u minus v is 0. That's true if and only if u equal to v. U minus v is 0. That's true if and only if u equal to v. So distance from u to v is 0 if and only if u equal to v. That completes the proof for part D.